Again. Okay, good morning. So here we are. It is June 16th, 2016, and let us continue our work on the equilibrium of rigid bodies. Alright, so from the Beer Vector Mechanics book, we have this problem here. This is problem 4.10. Let's see. The maximum allowable value of each of the reactions is 180 newtons. Neglecting the weight of the beam, determine the range of the distance d for which the beam is safe. So we have a beam with loads here and a variable distance d. So we have a beam with 3 loads on it and a variable distance d. And what we're going to need to do is we're going to need to say, okay, each of these supports can only support a reaction of 150 newtons, or sorry, 180 newtons. So we need to make sure not to exceed that on any one of them. So in other words, we're actually going to need to calculate these reactions, not just in terms of a static reaction, but in terms of as a function of d. So let's do that. So let's look here. So we have a free body diagram. Let me modify this to make it a free body diagram. I'm going to purposely neglect the x reaction on here because I know that this. Okay, actually, let me not neglect it. Let me show this here. I'm going to call this AY, BY, and BX. And these are our reactions. However, I know BX is going to be equal to 0 because there are no horizontal loads upon the structure. How did I get these? Well, if you remember, this is a roller here, so it can only support a reaction that is perpendicular to the surface. This pin, however, will be able to resist both an X and a Y reaction, so I need to draw 2 of them. And so this is how this is the usual notation I use for my reactions. I say the reaction joint and then a subscript of the direction. So this is the reaction at joint A in the Y direction. And I'm going to use principles of moments or sum of forces in the vertical direction to find the value of each of these reactions, but only as a function of d.
So if you have a pen, you put your xy's there?
If I have a pin, I put my xy's there?
Yeah,
Yes, yes, yes. If I have a pin, you will have both an x force and a y force there.
On a roller, you will only have the y.
On a roller, you only have the y. However, you got to be very careful, though, because there would be an exception to that, in that sometimes you actually can have a roller on a vertical. What if you have a roller on a vertical surface? So you have a beam like coming in like this, and there's a roller here, like that, this kind of thing. We have a beam, kind of a weird beam like this, like an L-shaped bracket, and then a roller here. Here you would have only an X, but not a Y. Okay. But anyway, let's look at this. So I'm going to do the following. I'm going to do, let's try doing a sum of moments, about B. Let's see what happens. So I'm going to say the sum of moments about B is equal to 50 newtons, counterclockwise positive here, 50 newtons times a distance of, let's see, 900 millimeters. 900 millimeters. Then 900 millimeters, let's see, 900 millimeters minus 100 newtons times a distance of 450 millimeters. Huh? Oh, thank you, sorry. The 100 newtons should be a pot plus, yes. I'm going to go ahead, you know what, I'm just going to go ahead and change these to meters, just for simplicity's sake. So I'm going to make this 0.9 meters. 0.9 meters, save some space, 100 newtons times 0.450 meters. And this force here will not generate a moment about B because it has no moment arm. This force here, the 150 Newton force, will not generate a moment about point B because its line of action passes directly through point B. Again, what I'm using here is the method of perpendicular distances. So the 50 newtons, the perpendicular distance from its line of action to point B is 0.9 meters. And then the same thing here. Then I simply have AY minus AY times a distance of that's going to be 0.9 minus D. And all of this is equal to 0. So questions how I got this.
I think it's the negative AY 0.9 minus D.
Okay, the negative AY 0.9 minus D. The reaction, we're summing moments about point B. The reaction force here, the force itself is AY. The magnitude of the force is AY. The distance from here to here, the perpendicular distance, is going to be 0.9 meters, which is the distance from here to here, minus D. Okay? All right. So now I just need to do a little algebra to solve this for, let's see, so solve this for AY. Yeah, I think that's what I'm going to do. Let's see. So let's look at this. I'm going to get, we will later take the moment about A, yes. We can actually take moments about any point. It's just a matter of there are certain locations that it's more advantageous to take moments. I took moments about point B because then that eliminates the reaction from point B into that equation, yes.
Would it be useful at all to sum the forces in the Y?
We could sum the forces in the Y, but the problem with that is that then we'll have two unknowns in the equation.
Okay.
50 times 0.9. Okay, that's just going to be 45. This is 45. This is 45. So this is going to be a total of 90. 90 Newton meters minus AY times 9 minus D is equal to 0. And I'm going to try to solve this for AY so I can set up a little inequality. Okay, so here, let's just do 90 minus 9AY. Actually, you know what? I probably don't want to do that. Let me erase that. I need to put this term over there. Let's say, AY times 9 minus D equals 90. Yeah, that makes me feel better. And then AY, I'll put it on the other line. Nope, I don't. And that leads us to AY is equal to 90 over 9 minus D. Just algebra. Let's see. Huh? 0.19. Oh, 0.9. Thank you. We got some 0.9s. We forgot some 0.9s, yes. 0.9. Okay, 0.9. Let's see, so that will work. And now I need to take this and say, hey, look, this expression here has to be less than or equal to 180. Because we're saying we're restricting the reactions to 180 newtons. So we know that this has to be less than or equal to 180. We should probably actually do even, we should probably actually even say it has to be, could also be that in the positive or negative direction, but I think it's safe to say that AY is pointing upward. And somehow my reaction got erased here. AY. So then let's work through the math. So we're going to say 90 is less than or equal to, actually let me just go ahead and make this, I'm going to move this over and divide by this. So I'm going to divide both sides by 180 and multiply both sides by 0.9 minus d. And I will get 0.5 is less than or equal to 0.9 minus d. And then from this, I will get, let's see, negative 0.4 is less than or equal to negative d, right? And then d is greater than or equal to 0.4. Okay, questions on that? But that's only part of the problem. We also need to solve for any restrictions based upon moments we also need to solve for restrictions based upon the reaction at B. Okay. So now I'm going to solve for reactions at, I'm going to do a sum of moments at A. So let's do a sum of moments about A. Well, if we sum moments about A, counterclockwise positive, I'm going to end up with 50 times D minus 100 times, this is going to be 0.45 minus D. And then, let's say, minus 150 times, let's see, it's going to be 0.9 minus D, plus by times the same 0.9 minus D. And that equals 0. What a mess. Okay, so let's see here. Well, let me just try to gather up some terms really quickly here. Here I have 50D. This is going to be essentially minus 100, minus negative, so it's going to be plus 100. So these two together are going to give me a plus 150D. This is going to give me 250D, actually a total of 300D. And this one is just going to, well, yeah. So 300D, and then minus 45, minus 45, right? No, minus 450, 0.9 times 150, 135, sorry. Oh, let's see, 0.9 times 50. Okay, that's, yeah. So we'll have the negative 100 times 0.45 minus 135. So I'm getting negative 180. That is the negative 100 times 0.45 and then minus 135 from here. And then let's say minus by d equals 0. Questions on how I got this far? Basically just doing an exercise of gathering like terms. Yes? Is there a, oh, the 0.9 by, yes, actually good, thank you. My 0.9 by, just, you know what, I'm just going to go ahead and leave this as unfactored, unexpanded, sorry. So let's just say plus by times 0.9 minus d equals 0. And then by must equal 180 minus 300d over 0.9 minus d. I like that. And by also has to be less than or equal to 180. So let's say this has to be less than or equal to 180. So that will lead us to oh, let's see, 180 minus 300d. Let's see, then I multiply this thing over here, 180 times 0.9. I'm going to get less than or equal to 162 minus 180d. And then I'm going to come up here, because I'm running out of space here. And so I will then, I'm going to add 360d to both sides and subtract 162. So that will give me 180 is less than or equal to, going to add that, so that will be 120d, positive 120d. And so then d must be greater than or equal to 180 over 120, or greater than or equal to, huh? Oh, 180 minus 160. Oop, derp. Let me double check that math. Let's say 180 over 162. Oh, I was thinking 18, not 180, sorry. So then d is going to be greater than or equal to 18 over 120, or simply 0.15. And that's the general format. Now, this is probably not the complete solution. What you'd actually want to do is we would also want to check for saying that it has to be, notice we only said that AY has to be less than or equal to positive 180. We should probably also go through and use the case that AY is greater than or equal to negative 180. And the same thing with BY here. We should probably also check if BY is greater than or equal to negative 180. Because we checked the positive case, but it could just as well be the opposite case, the negative case. So we should probably check both of those, but I think since I've done this far, I think that's good enough. I think you get the idea. Questions on this? Mm-hmm.
Your first dimension that we got from AY is reversed, right?
The first dimension for AY.
It should be less than. We have two greater thans now.
Not necessarily. I mean, it's quite possible just the way the math works out, that's the way it'll work out.
So D can be either greater than 0.15 or greater than 0.4.
The restriction, okay, the question, someone's confused that we have, the question is, someone's confused that we say, hey, look, how can we have both greater than 0.15 and greater than 0.1, then greater than 0.4? Well, this would set, this is a subset, this basically is a subset of this. So we would restrict this to say, oh, D is greater than 0.4. This is the controlling case here. Okay, other questions? Okay. Because we can't, essentially these will give us limitations, and we have to choose our most stringent limitation. So if any one of the reactions is exceeding our boundaries, then that becomes the controlling case. So it doesn't matter. It is not saying that, oh, D is both greater than this and greater than this. They don't necessarily have to have a less than and a greater than. We could simply have something like that. Now, I imagine if we did do something like this with the AY is greater than negative 180, that's probably where we'll get something with a less than. Yes?
So you're going to get two answers, but those aren't the two answers you're going to get. You're going to just say that 0.4 is the limitation.
Not necessarily. You have to actually look at the numbers and just interpret it from, principles of Algebra 1 and basically say, how is our domain limited?
Mm-hmm.
Okay?
Yes.
When you divide by that final negative,
Mm-hmm.
If you go back to
doesn't it switch the sign?
Divide by which final negative?
For the D greater than 0.4.
D greater than 0.4.
I'm thinking
Here?
it's supposed to go the other way.
switch sides.
Oh, did I miss that up? I may have missed that up. Okay, let's see here. Ah, there we go. Yeah, that will do it. Okay, so it was like this, and then, oh, yeah, that'll do it. Okay, that would make sense. So then D is going to be less than. Thank you. So yeah, what we have right here is a range that says basically D is between 0.4 and 0.15. However, we don't know if that's really the true range. We'd also have to check it for the negative condition, but I think we've gone far enough on this. Okay. All right, other questions? All right, moving right along. The rig shown consists of a 1,200-pound horizontal member, ABC, and a vertical member, DBE, welded together at B. The rig is used to raise a 3,600-pound crate at a distance 12 feet from the vertical member, DBE. If the tension in the cable is 4 kips, determine the reaction at E, assuming that the cable A is anchored at F as shown as in the figure, or B, anchored to the vertical member at a point located 1 foot above E. All right, so let's see. So X is here is 12 feet. We don't have to have an X, we have a 12 feet. Now, let's see. Let us look at this in terms of a free body diagram here. So let's call this force, I'm going to call this force here tension. And perhaps I'm going to have this weight 1,200 pounds. And then I have the 3,600-pound weight here. You know what? What just happened? I think I might need to draw this a little bit bigger. So we're going to have the crane here. And then we're going to have the forces here. So I'm going to have this force here that I'm simply going to call tension. Then I'm going to have EX, EY, and ME, the moment at E. Then I'm also going to have the weight here, 1,200 pounds, and 3,600 pounds. 3,600 pounds here. And the distances here are going to be a distance of 6.5 feet and 12 feet. And let's just go ahead and say this, if this whole thing is 12 feet, then this has to be 5.5 feet. What do you notice about my free body diagram? This is my complete free body diagram. Am I missing something? The ground's right here. The tension here. Do I need those tensions?
No, that's what I was about to ask.
You actually don't, and here's why. These are what I might call internal tensions, forces internal to the object. See, look, if I could draw a tension vector here, but I'd also have to draw a tension vector here, so basically down to here and down to here. Those are going to be the same force. So the tension force is going to pull on it here and pull on it here, but those two vectors are going to cancel themselves out. Same thing here. This one's pulling up on this end's pulling down on this end, but they're going to cancel each other out. So I'm not going to bother drawing internal member forces or internal tension forces that aren't going to interact with the outside of the structure. I'm only concerned with reaction forces right now, because that's what I'm trying to find. And they actually told us that the tension in the cable is 4 kips. Okay, so let's figure this out. So first I'm going to do part A. So let's, yes. X is 12 feet, right?
17.5 minus 12.
No, see, look. Look.
17.5 minus 6.
17. No. 17 is the entire going all the way out to the boom. I don't care about the end of the boom though. All I care about is the distance from here to this one and to this one. I'm not concerned about the end of the boom right now. These are the distances to the forces. The distance to the 1,200 pound force from the central vertical is 6.5 feet. If this whole thing from here to here, okay, just ignore that. It doesn't matter. We're actually not going to need it for this problem. This is actually so this is just going to be 12 minus 6.5. This thing here is 5.5. That's it. Okay, so first I'm going to say, all right, well, it wants us to explore getting the reactions in each of these cases. Yes?
I'm sorry. I didn't it said it's the tension in dBE, so how do you know that the tension is hanging off that side?
dBE.
dBE, so it's going straight down the y-axis.
The rig is being used to raise 12 feet from member dBE. What's the question?
Why? How do you know that the tension is coming off that side?
It's a rope. It's on a pulley. It's right there. Okay. So I have the following. Let me first just do a sum of forces in the horizontal direction. Well, if I do a sum of forces in the horizontal direction, the only force I have acting in the horizontal direction is Ex, and it is simply 0. Then if I do a sum of forces in the vertical direction, okay, I'm going to get negative 3,600 minus 1,200 minus 4,000 plus EY equals 0. And therefore EY has to equal, let's see, that's going to be 4,800, 8,800, right? 8,800 pounds. So the vertical reaction at Y is 8,800 pounds. Oh, we're still in part A here, I guess. Okay. So that's that. And then finally, let me do the sum of moments about point E. All right, let's see. So these two forces won't contribute to the moment, but I will have 1,200 pounds times 6.5 feet plus 3,600 pounds times 12 feet minus, let's say, 4 kips. Oh, and this, I should probably put the distance here. I do need this distance here. And this distance is 3.75 feet. So minus 4.75 kips times 3.75 feet. As a reminder, how do I know whether it's going to be positive or negative? Huh? Yes, whether it's positive or whether it's clockwise or counterclockwise. If the force about the point that I'm considering the moment, if the force wants to cause a rotation clockwise, like this one, it will be negative. If it wants to cause a counterclockwise rotation, it will be positive. Okay. Oh, and we have one other thing. Huh? Just P? Finally, plus ME. This is the actual reaction moment at this point. So finally, ME, well, I just sort of add 4 times 3.75 minus 12. Let me just go ahead and do this in terms of kips. Times 6.5 feet minus 3.6 kips times 12 feet. And this will come to 4 times 3.75 minus 12 times 6.5 minus 3.6 times 12. And I get negative 106.2 kip feet as the reaction moment at E. Questions on that? As the reaction moment at E, yes.
In the equation you wrote 12 kips, shouldn't it be 1.2 kips because it's 1,200 pounds?
Let's see. Oh my. Yes, thank you. 1.2 kips. Derp. That'll change things. Just, hey, what's an order of magnitude among friends? Just it's just a power of 10. Okay, so actually that changes the answer quite a bit. That's why you always check your math. So negative 36 kip feet. Negative 36 kip feet. All right. Unless we see any other stupid errors, that should be the answer. Or actually, better yet, it was always 36 kip feet. I have no idea what you're talking about. It was always 36 kip feet. Oh wait, this is being recorded. Crap. Pay no attention to the man behind the curtain. Alright, so let's keep going. Now let's do part B. Part B, we are asking, okay, we are now going, with part B, we are now extending this force, instead of this force attaching to the ground here, it is now simply being attached to the vertical member. Well, now this no longer is an external force, so it's not going to affect the reactions at all. Now we would have one force vector coming up from this point, another one coming down from this point. They're again going to cancel each other out. So this, so the free body diagram for part B here is actually a little bit simpler. It's just the same free body diagram, but without this force here. So I'm still going to have the 3 reaction forces. It's going to be the 3.6 kips, the 1.2 kips, and then I'm going to have the ME, the EX, and the EY. The EY here. So it's basically the exact same thing as this one, except the tension force here disappears. So the sum of forces I'm going to just neglect the X, it's obviously 0. The sum of forces in the Y direction is going to be negative 3.6 kips minus 1.2 kips plus EY. So EY will be 4.8 kips. Sum of moments about E. It's going to be the same thing as before, except just without this term here. So 1.2 kips times 6.5 feet minus 3.6 kips times 12 feet plus ME. And ME, therefore, is equal to, let's see, oh, this should be plus. So ME is going to be, and this is equal to 0. So ME, there should be a 0 here as well. So ME then is going to be equal to, let's see, negative 51 kip feet. Negative 51 kip feet. So notice what we've done. Notice what this rope allows. Notice what anchoring this into the ground allows. We essentially have two different choices here. We have two different systems that we could support this crane with. One, we're supporting it with the anchoring point on the ground. The other, we're supporting it without. Here we have a higher vertical reaction, but in turn, what we get by having a higher vertical reaction. So notice the vertical reaction at point E, in this case here, is a full 4,000 pounds higher than the vertical reaction in this point here. So that's the trade-off. That's what we're paying. But what do we get? For that, we get a drastic reduction in the moment. So notice the reaction moment here is 36 kip feet. Here it's 51 kip feet. So we've essentially traded one for the other. We've gotten more reaction force, vertical reaction force, but in turn we've been able to reduce our reaction moment. So depending on which one you want, you can trade off back and forth. Yes.
Since this is a rig, you probably want a big reaction moment, right? So it can pull heavier.
No, I mean the reaction. The question is, hey, this is a rig. You want a big reaction moment, right? Well, no. I mean, ultimately, you want ultimately you want as small a reaction moment as possible.
Okay.
You have yes, if you have a bigger load, that simply means you have to carry a larger reaction moment generally. But
Okay.
always the bigger the moment in that connection, the more steel it's going to take, the heavier that connection is going to be. So so it's hard. So I have a hard time saying, oh, that's a more reaction moment. That's a good thing. Yes.
B was asking for the moment without tension cord.
Look what it's asking.
Yeah.
Attached to the vertical member at a point 1. So basically, it's attached right here. And the reason that force doesn't appear on that is because it now becomes an internal force. On the free body diagram, we're only drawing forces that are external to the body. Only drawing forces that are external to the body. It's kind of like, the reason I'm not drawing these forces, it's like, imagine trying to lift yourself up by pulling up on your own feet. Imagine trying to lift yourself up off the ground by pulling up on your own feet. Why doesn't that work? The reason that doesn't work is because those are internal forces. Now, I suppose if you could actually lift yourself up if you used like an elaborate like pulley mechanism or something like that, right? But then you're not reacting off of yourself. You're using external forces. Then you're actually using, say, a pulley on the ceiling or something. But obviously, yes, you know from experience, obviously you cannot yet lift yourself up off the ground. That's obviously not possible. So, and the reason for that is because just as much as you are pulling up, you are by pulling up on your own feet, you are in turn pushing down even harder through the soles of your feet. So your tension force is internal. It's not really a really external force. With free body diagrams, we're only drawing external forces. Which is why, for example, you've probably seen something like this before. I mean, hey, I got a great idea, right? If you have a sailboat, I mean, can't we just, if we want to make the sailboat go faster, why can't we just, oh, I don't know, I'll just put a thing here. Does that work?
No.
Can I just put a big old fan on a sailboat and make it so I can go faster? Why not? Why doesn't that work?
Equal opposite.
Equal and opposite, yes. Yes. This is basic Newtonian mechanics here. Equal and opposite forces. So yes, this fan here will generate wind, and this will actually produce a force in this direction on the sail. However, in order to actually accelerate the air that much, in turn, an equal and opposite force will be exerted on the boat here. If anything, this would actually cause the boat to slow down, probably. But okay. Anyway, this is a bit of a silly example. The whole point of this is to illustrate why we're not considering internal forces on our free body diagrams. They are not going to, if this was a free object, these forces would not go toward accelerating the object. Therefore, they will not contribute to the reaction forces for a stationary object. Yes?
When I see that we have a negative moment about E, that makes me think that the forces is causing the crane to rotate clockwise from our perspective?
Okay, the question was, hey, we have a negative reaction moment. Does that mean the sum of forces is causing a clockwise rotation? No. And the reason for that is actually, altogether, these are actually clearly causing a counterclockwise rotation, right?
Oh, so that even, okay.
The reaction moment is what moment you need to apply to it to prevent it from moving. So the forces on here, with these two forces, without the reactions, have a tendency to cause a counterclockwise rotation. But if we want to stop that, we're going to have to apply a clockwise rotation. So, in other words, the reactions are what forces need to be applied at the support points to prevent the object from moving under the forces that we've drawn on the free body diagram. Okay. Other questions?
E is statically determinate.
This whole problem is statically determinate, yes. Because it has 3 unknown forces, yes. Okay? Other questions? All right. Fun. Let's get rid of that. Okay. All right. So we've gotten through a lot of chapter 4 already for the basics of equilibrium. Again, the key to equilibrium, we've discussed this, is for rigid bodies, sum of forces x equals 0, sum of forces y is equal to 0, and then obviously sum of moments equals 0. This is for the 2D case. And then for 3D, we simply add another force and 2 other moments. Sum of moments x equals sum of moments y equals sum of moments z equals 0, and sum of forces in the x equals sum of forces in the y equals sum of forces in the z, also equal to 0. And this is the 3D. But this is just obviously a brief repeat from last time. Okay, so there are 2 special loading conditions I want to consider. This is what's known as the 2-force body and the 3-force body. So, 2-force bodies. Let's consider another potato. I'm going to draw another one of my favorite potatoes. So an arbitrary object with 2 arbitrary forces on it. So we have 2 objects. So we have 2 forces that are just arbitrary forces on this body. This body is called a 2-force body simply because it has 2 and only 2 forces on it. Realize this object doesn't even have self-weight. It's an idealized object. There are only 2 point forces acting on it and nothing else. Okay. So here's a question. As drawn, can this be in static equilibrium? Why not? Huh? Why? Okay, the question is, you don't necessarily have to have 3 forces on an object to be in static equilibrium. You're thinking reaction forces. Well, okay. Back up. Let me just say, let's ignore reactions right now. Just as drawn, can this be in static equilibrium?
Yes.
It actually can't. Any idea why?
So what if
Or this will not be equal to 0.
Huh?
They will not be equal to 0.
Well,
oh yeah,
The X
yeah.
components
No,
would
it
never.
can't.
well, okay. So the question was, can this be this can't be in equilibrium because someone responded, this can't be in equilibrium because the x components clearly aren't equal to 0. So clearly, by the sum of forces in the x and y direction, we can say, oh, the basically f1x must equal negative f2x, right? and f1y must be equal to negative f2y. In other words, the x and y components must be equal and opposite, don't they? The x and y components must be equal and opposite. Okay, so that's something interesting to know.
But no matter what, will it cause rotation?
Ah, that's the question. What about rotation? What about rotation? What about rotation?
Well, since it's not a point particle.
What about rotation? See, here's the thing. Huh? If I restrict it to this case, then, so let me draw it restricted to this case here. Let me draw another potato restricted to this case. So now I'll draw two that are, I'm going to try to draw these approximately equal and opposite. F2 and F1. So yeah, it's basically a couple. So yeah, now we basically have a couple. Uh-oh. Now we have a couple. That's definitely going to rotate, isn't it? It's a couple. It's definitely going to rotate. So how can we, what's the only way you can prevent this from rotating?
Collinear. Oh, what's the other?
Switch the direction of one.
Same line of action.
We could make them, we could reverse the direction on this, but then it won't be, if we reverse the direction on this one, then it would no longer rotate, but now it would translate. So instead we need to make them collinear. So basically we start with this generic case, then this causes us to narrow to this one, and then we say, oh, wait a minute. They have to have, their lines of action have to go through each other. That is the only way this thing won't rotate. So must be collinear. Collinear to prevent rotation. To prevent rotation. They must be collinear to prevent rotation. So therefore, it now becomes something like this. Another potato. Here. So something like this. F2, F1, like that. So in summary, two force members, or two force bodies, must have equal and opposite forces on the same line of action. And this will be very important when you start talking about trusses. Equal and opposite forces on same line of action. Equal and opposite forces on same line of action. On the same line of action. So this is just a theory type thing. Questions on that? Okay. So let us look at three force bodies. This is another case. And you can read about these in greater detail in your book, but just an interest. This one is a little bit less important, but I do like to mention it. Okay, three force bodies. You can see a discussion. You can see a discussion on page, I believe, let's see, 184. But the basic idea of this, based upon similar principles, is I'll just mention it briefly before. I think I want to spend more time just working on examples today, but briefly I'll just mention that in order to be in equilibrium, the three forces on a body, the three forces on a three-force body must all have intersecting lines of action. And why is that? I can describe it very briefly. This isn't exactly a rigorous proof, but I'll describe it briefly. Okay. So say I had three forces that didn't line up anywhere. So say this one's line of action goes here. This one's line of action goes like this. They meet up here, but then I'm going to purposely draw one whose line of action goes like that. See, if I sum moments about this point here, this one and this one won't be able to generate any moment about that point because their line of action both passes through there. So their moment arm about this point is 0. If I sum moments about this point, here, can you see this little triangle here that I'm talking about? Okay, if I sum moments about this point here, then this force and this force will not generate a moment there, but this one will, and there's nothing to then resist that. If I sum moments about this point, then this force and this force will not be able to generate a moment there, but this one can, and there's nothing there to resist it. So we can't have a lone force out there with nothing to resist it if this is supposed to be in static equilibrium. So therefore, instead, we end up with something like this. For a real three-force body, they must have, all of the lines of action must meet at some common point. Now they don't have to be, the three-force body doesn't say anything about the magnitudes of the forces. It simply says that the lines of action must meet at some point. That way, we will not have only two not generating moment at one point. All three of them will not generate any moment at that one point. All right, yes.
This is the case for 2D and 3D.
With 3D, it gets a bit more. You'd get a bit more complicated, but yeah, this is generally concerned strictly with 2D right now. Okay. Other questions on this? Okay. I have a few more. I think I'll work through one more example, then we'll, again, like I said, today I'm going to mainly be working through example problems is how I foresee today. I think I'll work through one more example, then we'll take a short break, come back and work on more examples. So, is that okay? Okay. I don't have quite as much theory to work through today as I sometimes do, but
You didn't work a problem last time.
yeah, I didn't work through a problem last time. So actually what I've done is I still have the problems from yesterday that I was going to work through yesterday if I had time, and then I have some extra problems too. So I have a whole bunch of problems to work through today. The material from chapter 4, the actual theory of it, like where I write out things like, you know, this kind of stuff, it's not that complicated. But actually the real difficulty of this chapter of taking equilibrium of rigid bodies is merely gaining enough experience working through different types of problems. So that's what I want to do today, just work through as many problems as I can. Okay, so let us look here. Start of chapter 4, problem 4.4 here. For the bracket and loading, let's say, let's see. Okay. Let's see. A T-shaped bracket supports the load shown. Determine the reactions at A and B if A is 10 inches and B is 7 inches. Okay. A is 10 inches and B is 7 inches. Okay. Or if A is 7 inches. Let's see. Determine the smallest distance Okay, maybe I can work through both four. Let me start by working through 4.3 here. 4.4 is a modification of 4.3. So let's just work through one of these. Or would you rather me work through 4.4 or 4.3?
4.3 was the homework you got.
Okay, you'd rather me work on that one? Any preference?
Do 4.3, we got the notes.
Huh?
Is it
We
one
have
of
the
the,
notes on 4.3.
You already have the notes on 4.3? Okay, so I'll do 4.4. Okay, so let's do 4.4. So essentially what's happening here is we don't need to worry about this. We just have the T-shaped bracket with the 4 forces on it. So determine the smallest distance A if the bracket is not to move. Okay, so what that tells me is the following. So let's look at the forces here. This is a pin, this is a roller. So here I have Bx, here I have By, and here I have, okay, here's the thing. I'm going to draw this like this. Ay. I know that as this is drawn, this thing will not be able to pull up. So it must be applying a downward force to this bracket, this T bracket. So I'm now going to do a sum of, let's see, how could we do this? I'm going to take a sum of moments. So we don't know A. We're going to try to find the smallest A such that this does not move. Now,
that's a B is a pin?
B is a pin, yes. Now here's the thing though. Here is the question. I want to find the smallest distance A for this bracket not to move. However, I want to do a sort of thought experiment. What happens if I were to make A very, 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 very large? I stretch this thing out so it's way, way, way over here. Well, these two forces here are obviously going to completely overcome the moment generated by these forces, right? And so this thing is just going to really crank down, and this thing is just going to be supported. This is going to have an enormous. This roller would have to apply enormous downward force on this to keep this thing stationary, right? So, in other words, I'm trying to find out a boundary condition, and that boundary condition would be these. Would you concur with me if I said the smallest A will be when AY is 0? Would you agree with that? See, if this could actually support if this could actually apply an upward force, well then I could just make A be right equal to 0. It could just keep this thing from rotating in the other direction. It wouldn't be a problem at all. But because it can't, the smallest force will be where this is 0. The smallest, A, will be where this is 0. You kind of see where I got that? Okay. So this way I don't have to solve for a bunch of less than or equal to's. I can just say, oh, the smallest will be when AY is 0. So now I can just go there, goodbye. I don't need to worry about you anymore. So instead, the moments are going to actually sort of balance each other out. So now I simply solve for A. So let me do a sum of moments about point B, counterclockwise positive, of course. And I no longer have to worry about this force. So I'm going to have 40 pounds times 6 inches. This one won't generate a moment about B. Minus 30 pounds times the distance A. Minus 10 pounds times a distance, let's say A plus 8. And all of this is equal to 0. So 240 minus 30A minus 10A minus 80 equals 0. Minus 40A plus 160 equals 0. A equals 4 inches. Concur? Again, all I did was set set the force at support A equal to 0, and then solved for A. All right, questions on that?
Can you use a pound sign to express pounds? Like,
Yeah, I've seen that done before.
That interesting.
The question was, can I use a pound sign to express pounds? I've seen that done before. I've seen plenty of people do that before. Why not?
I kind of want to do it.
So yeah, you can say, 8K for kips, 8 pound for pounds. Why not?
You normally do it in superscript as well.
It's all good. I've definitely seen that before. Okay, other questions? Okay, let's come back. Let's go take a short break, then come back, and we'll look at some more fun examples. The question, okay, for those, if you didn't catch that, the question was, can I just write pound signs like that? And yes, you can. Sure, why not?